Hey everyone, Nicola here from CalcuNick, and today we're going to talk about the squeeze theorem. Let's get right into it.
Okay, so let's talk about the squeeze theorem. It goes as follows. Say we have three functions, f, g, and h, and they're defined on some interval I. Now, if for each x, where x is an element of I, g of x is less than or equal to f of x is less than or equal to h of x, and the limit as x goes to a of g of x is equal to the limit as x goes to a of h of x is equal to some number L, then we have that the limit as x goes to a of f of x is also equal to L. Now, that was a lot of words, so let's try to express this geometrically and get a better picture. Here we have the three functions g, f, and h, and on some interval. We see that g is always less than or equal to f, and f is always less than or equal to h. And furthermore, at the point x equals a, we have that g is equal to h, and is also equal to L. And by the squeeze theorem, we have that the limit as x goes to a of f of x is also equal to L. Let's see if we could use the squeeze theorem in some examples. Let's say we're asked to prove that the limit as x goes to 0 of x squared times sine of 1 over x is 0. Usually for these questions, we would go by inputting x equals 0 for every occurrence of x in the equation. However, sine of 1 over x when x is 0 is undefined, so we can't do that. We now consider the squeeze theorem as an alternate method to solve these kinds of problems. Usually, we'll start with a term that yields an undefined result with the squeeze theorem. So in this case, this is sine of 1 over x. So we'll write that down. So we have sine of 1 over x. Now, with trigonometric functions such as sine and cosine, it's important to remember that they always output a value in between -1 and 1. And we'll add those restrictions here. Now that we have our first step, our goal now is to somehow make this expression look like this by adding or multiplying various terms. Well, we notice that we're just missing a term of x squared in this, so we're going to multiply our entire equation by x squared. We write minus x squared is less than or equal to x squared sine of 1 over x is less than or equal to x squared. Now we have our first step in using the squeeze theorem. We've shown that the equation we're trying to prove is strictly in between two other equations, in this case minus x squared and x squared. Let's see if they have the same limit when x is 0. Thankfully, they do. We have that limit as x goes to 0 of x squared is equal to 0, because 0 squared is 0, and that's also equal to limit as x goes to 0 of minus x squared, because minus 0 squared is still 0. And therefore, we could write by the squeeze theorem, we have proven that the limit as x goes to 0 of x squared times sine of 1 over x is equal to 0. In this question, we're being asked to prove that the limit as n goes to infinity of 2 minus 4 times -1 to the n over n is equal to 2, and where n is an integer. Notice that we are working with an infinite limit, and although the definition for squeeze theorem with infinite limits is slightly different, the logic is essentially the same. As before, we're going to start with a term that gives us trouble, and that's -1 to the n, as -1 to the infinity is undefined. So we have -1 to the n, and this is clearly less than 1 and greater than -1. Now, what we want to do is take this term and add on some terms to it to make it resemble our final equation. To do that, first we're going to multiply by -4 and divide by n. So on the left-hand side, we have 4 over n is greater than or equal to, because we multiplied by a negative number, so we switch the inequalities, -4 times -1 to the n all over n, and that is greater than or equal to -4 over n. Now, to make this look like the expression above, all that remains is to add 2 to all the sides. So we have 2 plus 4 over n is greater than or equal to 2 minus 4 times negative 1 to the n, and all of that is over n, which is also greater than or equal to 2 minus 4 over n. Now, we have step 1 of the proof by squeeze theorem completed. We have our set of inequalities. Now we want to show that the leftmost inequality and the rightmost inequality have the same limits when n goes to infinity. First, we have the limit as n goes to infinity of 2 plus 4n. And when we take 4 over infinity, that's just 0, so this is equal to 2. And sure enough, it's the same story for the limit as n goes to infinity of 2 minus 4 over n, because 2 minus 0 is still 2. And so we have finished our proof by squeeze theorem, and all that remains is the concluding statement. Therefore, by the squeeze theorem, the limit as n goes to infinity of 2 minus 4 times negative 1 to the n over n is equal to 2.
Our last problem asks us to prove that the limit as x goes to infinity of 3x squared times sine x plus cos squared x all over x cubed plus 1 is equal to 0. At first glance, this question looks pretty tough and maybe even intimidating. However, if we stick to the basics, it's really not that bad. As always, we look for the term that we could create a boundary for, and in this case, it's right here. We'll look at these two separately and then bring them together. So first, just the same as before, we have sine of x, and this is obviously always less than 1 and greater than negative 1. Now, if we look at cos squared x, it's really similar to sine x. However, it's always going to be greater than 0, not negative 1, because any negative output will be turned positive by the square. And still, it's always less than or equal to 1. And so, when we bring them together, we'll get that negative 1 is less than or equal to sine x plus cos squared x, which is less than or equal to 1 plus 1, or 2. Now, we have our basis, and we want to transform this to look something like this equation. So let's start with that. We'll divide both sides by x cubed plus 1 and multiply both sides by 3x squared. We get the following result. On the left-hand side, we have x cubed plus 1 and all over negative 3x squared. This is less than or equal to 3x squared times sine x plus cos squared x, and that's all over x cubed plus 1. And finally, our right hand side, we have x cubed plus 1 in the denominator, and we have 3x squared in the numerator. So now we're going to look at these two terms and see if they have the same limit as x goes to infinity. So first we take the limit as x goes to infinity of negative 3x squared all over x cubed plus 1. Now we're going to divide both top and bottom by x squared to get the following result. We have limit as x goes to infinity of minus 3 and divided by x squared, so just 1, all over x cubed over x squared, or x plus 1 over x squared. And now we could replace the occurrences of x with infinity. Notice that 1 over x squared will go to 0, as 1 over infinity is 0, and that means that this whole result is equal to negative 3 over x, and negative 3 over infinity will also be 0. So this is equal to 0. And by similarity, you could also notice that the limit as x goes to infinity of 3x squared over x cubed, x cubed plus 1 is also equal to 0. Although I would not recommend doing that if you're in an exam situation. I would definitely write out all the steps just in case you wouldn't want to lose some easy marks on this. And so we could write our final concluding statement. And so, therefore, By the squeeze theorem, the limit as x goes to infinity of 3x squared times sine x plus cos squared x all over x cubed plus 1 is equal to 0. Alright guys, thank you so much for watching. If you had any questions, any comments, or you had any other suggestions for other videos, drop a comment down below. I do try to get to all of them, so hopefully I can make a video for you. If you like what you saw, if you feel like you learned something, consider leaving a like and a subscribe. It's not much, but it really helps me grow my channel. That's all from me. Till next time.